You are welcome to H2O channel, and today we are going to be doing physics. This physics by the H2O, and the topic we are going to consider today in physics is expansivity of materials. Like we all know, expansion simply means the increase in size of a material when it is heated. And don't forget that when a solid is heated, the solid material is heated, the material will certainly expand. Okay, so today we are going to be looking at the physics behind the expansivity of material. Okay, let me repeat myself again by saying that expansion means the increase in size. This increase in size can be length, it can be area, or it can even be the volume of the object. Okay, and that's what's going to give birth to the three types of expansivity, like we all know. Okay, now the types of expansivity, are given below. Okay, now the first expansivity that we have is called linear expansivity. Linear expansivity. Okay, don't forget that the symbol for linear expansivity is alpha. This is a Greek alphabet. It's called alpha. This is the symbol for linear expansivity. Okay, now what does linear expansivity mean? Linear expansivity simply means the increase in length per unit length per degree rise in temperature. I repeat again, linear expansivity is the increase in length per unit length per degree rise in temperature. Okay, now from the definition you can coin the formula for linear expansivity. And what becomes the formula for linear expansivity? Very easy. It is stated that linear expansivity, this is your symbol. You can also call it the coefficient of linear expansivity. It says that it is an increase in length. The increase in length also means change in length. And change in length is given like this. Increase in length per unit length, that was dividing by the original length, per degree rise in temperature. Or rise in temperature is change in theta. So class, this is the formula for linear expansivity of a material. I think this is what we are going to be considering now before we can go to the other types of expansivity of material. Okay, now we're going to break this formula down so that you know how to apply your formulas. Okay, we are going to break what these variables and symbols signify. What does this mean? This simply means change in length. Change in length. And you know what change in length means? When the length of a material changes, it means it has either increased or reduced. Okay? Now, this change in length can be given as L2 minus L1. That's when there is an increase in the length of a material. Or the change in length can also be given as L1 minus L2. Now, the question given is what will determine the formula to use for your change in length. Remember that when we say material change in length, it's that there's an increase in the length or there's a decrease in length. When a solid is heated, it will expand. But on cooling, it will what? It will contract. So for that reason, we can have L2 minus L1 or L1 minus L2. Your L2 minus L1 simply means increase in length. Your L1 minus your L2 means decrease in length. In this case, it means that your final length is bigger than your original length. But in this case, it means that your original length is bigger than your final length. So you have to be attentive to details when solving questions, okay? Then remember, your L1 signifies your original length. L1 is original length. Original length, okay? Then what does this symbol mean? This delta theta. The delta theta here means change or rise in temperature. Change or rise in temperature. Now, your temperature here can be in Kelvin or in degrees Celsius. Please be attentive. Your temperature can either be in Kelvin or in degrees Celsius. As long as both temperatures are of the same unit, you don't have to convert to Kelvin. You don't have to convert degrees Celsius to Kelvin like you do in Charles' law. You don't have to do that. Okay? Then this your change in temperature. Remember, there could be an increase in temperature or a decrease in temperature. If there's an increase in temperature, it means that the final temperature is higher than the initial temperature. And that is what will give birth to theta 2 minus theta 1. Okay? But when there is a fall in temperature, it will give birth to theta 1 minus theta 2. Please, whenever you are solving questions in WAEC or JAM or other related exam, be very careful on how you do your subtraction. Remember what I told you. The temperature can either rise or fall. If it rises, it's theta 2 minus theta 1. If it falls, it is theta 1 minus what? Theta 2. Same with your what? Your length. There could be an increase in length or a decrease in length. Please be attentive to details. So what I'm going to do for you right now is that we are going to take 1 or 2 questions on linear expansivity of material from WAEC or JAM. Now we are going to solve this question from your JAM. This is University Matriculation Examination 1995, question number 26. We are going to solve this question on linear expansivity, so you can see how to apply the formula in your forthcoming examination. Okay, now look at this question, class. They said a metal has a linear expansivity of 0.0002 per Kelvin. Okay, what rise in temperature would cause it to increase by 1/10 of the original what length? And then you see the options given. Option A says 200 Kelvin. Option B says 250 Kelvin. Option C says 500 Kelvin. And option D says 1000 Kelvin. So if you are given a question like this, how do you solve it in your exam? Very easy. All you have to do is to first of all bring out your parameters or your variables that are given in the question. Okay? A metal has a linear expansivity. Remember I told you the symbol for linear expansivity is alpha, and is equals to 0.0002 per Kelvin. That's one. You go further. What rise in temperature? I told you that rise in temperature means change in temperature or increase in temperature, okay? So we are looking for delta theta. Please take note of this. This is what we are looking for. Then they said would cause it to increase by 1/10 of the original value. What rise in temperature will cause the metal to increase by 1/10 of the original value? Okay. Now, the 1/10 of the original value means that the change in length will become 1/10 of the initial length, which is L1. Remember, L1 wasn't given, so we can say that our L1 is what? Unknown. But they said that the change in length is 1/10 of the original length. So very easy to solve. Remember your formula that your linear expansivity is the increase in length per unit length per degree rise in temperature. So all you have to do is to put your values into the formula, then you get your answer. Remember, we are looking for delta theta, okay? Now, if you make delta theta subject formula, you remember that this delta theta will come here, we come over, just to cut it short, your alpha will come this way. So you can say that your delta theta is change in the original length all over original length times your alpha. Look at what I just did. It's not a magic. You can take this one, most of us are preparing for JAM, so you can take this one, put here, bring this one here. It's very correct. Okay, you don't have to follow that long procedure of making your delta theta subject formula. Okay, so let us solve this question now. Your delta theta becomes equals to, remember, the original length is the change in length is 1/10 of the original length. So put it here. We have 1/10 of the original length, L1, all over. Remember, L1 was not given, so we'll still leave it as our L1 times our alpha. What is alpha? Our alpha is 0.0002. So do it times 0.0002. Very easy. Please be smart. Remember, you are a JAM student, or if you are preparing for WAEC and you are given an objective question like this, you can use this to cancel this. Fear thou not is correct. Okay? So what do you do next? You do Remember, you have 1 over 10, and then you have over 1 divided by 10 all over 0.0002. Okay, so what you can simply do is this. This 1 over 10, this 10 can come down here. Remember, if you have A over B divided by C, here is the logic, class. You can do A over B divided by C over 1. Seeing that these two goes together. Okay, then you can from there have A over B. Remember, you were taught in elementary mathematics that when dividing two fractions, you turn the division sign to multiplication sign, and when that is done, you make the numerator denominator, and the denominator becomes the numerator. So you have A over B times 1 over C, and that will give us A over BC. Did you get? So this one is just a long process. What you simply do whenever you have a case like this is to take this one down so that you have A over what? BC. And that's what we are going to do in demystifying this question. We are going to do this. Remember, 1 over 10 all over 0.0002. So what would that give us? That will give us 1 over, this 10, bring it down. So you have 10 times 0.0002. And what would that give us? I think I have to create space for our board. Now it will give us, remember, 1 over 10 times 0.0002. If you multiply this, you are going to get, remember, we are looking for change in theta equals to 1 over 10 times 0.0002 will give you 0. You just remove one of the zeros. So if you have 1, 2, 3, 4, multiplying by 1 0, you remove 1. So you have 0.002. So that the total number of zeros will become 3. 1, 2, 3, 4 is what you have before. So you multiply by 10, it becomes 3. You can use your calculator to confirm it. And if you divide 1 over 0.002, you are going to get 500 what? Kelvin. So it's very easy to solve. Let's go back to the option and see our answer. Option A says 200 Kelvin. Option B says 250 Kelvin. Option C says 500 Kelvin. And option D says what? 1000 Kelvin. So our answer to this question is what? C. Thank you very much. Now we are going to take another question on linear expansivity. Although the two questions are even the same, because the first one we saw was from JAM. So this one is, we are going to take a question from XSC, which is NECO. So this one came out in NECO 2005, question number 20. How do we solve this? Very easy. Now let's go through the question so we know what to do. They said, when a brass of length 100 centimeter at 50 degrees Celsius is heated, its length changes to 100.054 centimeter at what? Now this question is trying to say that when the temperature was 50 degrees Celsius, the length was 100 centimeter. Now that the length is 100.054 centimeter, what will be the temperature? If you look at the options, you know what to do. The options are given to us in degrees Celsius. So what they are probably looking for is the final temperature, which is theta 2. So if you want to solve this question, it's quite very easy. Like I told you, the steps in solving physics problem is to first bring out your parameters. Okay? Now, when a brass of length 100 centimeters, that's the original length of the brass. So let's bring it out. Our L1 is equals to 100 centimeter. Okay? Now, at 50 degrees Celsius, that is to say, our initial temperature is 50 degrees Celsius. I've told you before, when you are giving questions in linear expansivity or area expansivity or volume expansivity, you don't have to convert the temperature to Kelvin. It's only in Charles' law and in the determination of the speed of sound in air that you have to convert to Kelvin. Now, they told us that the length now increased to this. So our L2 is 100.054 centimeter. They are now asking us to determine the second temperature, which is the final temperature. Did they give us linear expansivity of brass? Yes, it was given. Linear expansivity of brass was given. And what was linear expansivity? Look at it. They said that the linear expansivity of brass is equals to, look at it, 0.1234. 1, 2, 3, 4. Then you have 1/8 per Kelvin. I know some of you will be intrigued that the linear expansivity is given to us in per Kelvin, and because of that, you might be tempted to convert from degrees Celsius to Kelvin. You don't have to do that. Remember, a change in 1 degree Celsius is equivalent to a change in 1 Kelvin. So you don't have to convert from degrees Celsius to Kelvin. You solve that way and you get your answer. Now, we are going to determine our change in length. Remember, like I told you before, when there's a rise in temperature, the length will increase. So the change in length will give us the final length, which is L2 minus L1. And what is our final length? Our final length is 100.054, while our initial length is 100. So by the time you subtract, you are going to get 0.054 centimeter. That's what you have. So our change in length is 0.054 centimeter. Okay? If that is our change in length, we can proceed further. Remember, your linear expansivity is the increase in length, I've told you, all over the original length times your change in temperature. What were we told to calculate? You were told to calculate for the final temperature, which is θ2. But you cannot get your final temperature except you first get your change in temperature. So what I'm going to do now is to calculate for this change in temperature first. Then you can determine your final length. So how do we calculate for this change in temperature? Very easy. Make your change in temperature subject formula. Like I told you, you don't have to stress yourself. You can do the magic like this. Simply take your change in temperature this way and bring your linear expansivity this way, and that's all. So what we have now is that change in temperature will give us change in the original length over, remember, I told you to take this here and bring this here. It's like a magic, but it's possible. So you have L1 times the change, the linear expansivity. Now, if you have made this formula, you can impute your variables and get your answer. So your change in theta will give us change in length. What's change in length? 0.054 all over your original length. Your original length is 100 times your linear expansivity, which is 0.00. I think we have 1, 2, 3, 4. Okay, we have 4 zeros after the point. Please, for exam purpose, you have to count the zeros so that you don't make mistake. If you count 1, 2, 3, 4, okay, 1, 2, 3, 4, then 1, 8, 1, 8. Like I told you, what you have to do now is this. Here you have 0.054 all over. Remember, the number of zeros here is 1, 2, 3, 4, 5 all together, and you are multiplying with 100. Like I told you, the 2 zeros here can cancel 2 zeros. You can use your calculator to confirm that. So if you cancel 2 zeros, instead of having 1, 2, 3, 4, 5, you will now be having 3 zeros. So that will give us 0.00, which is 3, because the 2 here have cancelled 2, so you are left with 3. And if you are left with 3, make sure you have your decimal points at the first zeros. Then you can bring your 1/8. So what do we have to do now? We have to divide our 0.054 by 0.0018. I think we have to create a space where we'll do that. Okay? I think we have to do this. Let's finish our question here. How do we do it? We are going to divide 0.054 over 0.0018. So let's do it. 0.054 divided by 0.0018. When that is done, you are going to get your change in temperature equals 30 degrees Celsius. I know many of you will be quick to look for the answer in the option. Don't forget, you weren't told to calculate for the change in temperature. You were told to find the final temperature. Don't forget that. And you know that from what we did before now, that our change in temperature means theta 2 minus theta 1. Okay? So you are looking for this theta 2. So if your change in temperature is 30, you put it there. You are looking for theta 2. What's your initial temperature? It was given to us that it is what? 50 degrees Celsius. So you put your 50 degrees Celsius. So what do you do? Remember, if minus crosses this Red Sea, it's going to become plus. So you have 30 plus 50 is equals to theta 2. So finally, our theta 2 is equals to 80 degrees Celsius, and you have gotten your answer. So the answer is not A, please be careful. The answer is not B, is not C, but what? D. Thanks for watching this video, the H2O channel. Please do well to subscribe, share, and click the notification bell so you can always get our videos whenever we come online.